Hyperbolic geometry is a non-Euclidean geometry. So maybe it's time to revisit the Euclidean postulates in the context of hyperbolic geometry. So let's start with the first one. The first Euclidean postulate said that there exists a unique line joining any 2 points. So the question is, does this still hold on the hyperbolic plane? And a quick answer is yes. Any 2 points on the hyperbolic plane can be joined by a unique geodesic, right? Depending on their relative position. If this is the hyperbolic plane, x, y, if I have any 2 points, A and B, and they are directly on top of each other, then the unique line, the geodesic, is the vertical line joining them. On the other hand, if 2 points are not on the same, do not have the same x coordinate, let's say here's A and so I'm trying to join A and C, then you know that, well, if I connect these two like that and then draw a perpendicular bisector, here is a circle. Here's the center of a circle that connects both A and C, and this is the unique geodesic. Geodesic joining A and C. Right, with this one, the vertical line, so if this has some coordinates x0, y0, then this should have the same x coordinate, so x1, the same x coordinate, so x0, y1. Then this is also the unique geodesic. Joining A and B. So if we agree to replace the lines in the Euclidean postulates by geodesics, then the first Euclidean postulate still holds on the hyperbolic plane. Let's now look at the second postulate. The second postulate says that any finite line can be continued indefinitely in any direction. So postulate number 2, any finite line, remember for Euclid, line segments were actually called lines and there were finite lines. So any finite line can be continued indefinitely in any direction. Well, in any of the 2 directions. So let's see how the situation now looks like on the hyperbolic plane. So let's consider the 2 possibilities. Finite lines could of course be vertical or parts of these circles centered on the x-axis. So what happens if they are vertical? So if here's point A and point B, again they have the same x coordinate. So x0, y1, and A is x0, y0, then here's the geodesic. Alright, it's quite apparent from the picture that you can continue this geodesic indefinitely in the direction that the positive y-axis is pointing. But there seems to be a bound as you go towards the x-axis. But this bound is only illusory, because that we see this bound because we see the x-axis. And as we discussed in one of the earlier videos, the people who live on the hyperbolic plane can never see the x-axis. In fact, what's the distance, the hyperbolic distance between A and B, because they are vertically aligned, the hyperbolic distance between them is the natural log of y1 over y0. So extending the line in this direction means increasing y1. Extending the line in that direction means decreasing y0. Both of these make this distance go to infinity. So moving B up, moving B up increases y1 to infinity. So the limit as B goes, as the coordinate, right? So as B goes to B goes up, so as y1 goes to infinity of the distance between, let me just write now the coordinates, x0, y0 and x0, y1 is equal to the limit as y1 goes to infinity of natural log of y1 over y0. So if I keep y0 fixed and go with y1 to infinity, this is infinite, which means this line, as I keep going up, extends indefinitely to a geodesic of infinite length. And similarly, moving A down, but not below the x-axis, just towards the x-axis, decreases y0 to 0. So if we take the limit as y0 goes to 0 of the distance between these 2 points, where I now keep y1 fixed, so that gives the limit as y0 goes to 0 of natural log of y1 over y0. As y0 goes to 0, right, this thing goes to infinity. So the natural log also goes to infinity. So the conclusion is I can also extend this geodesic indefinitely towards the x-axis. It looks to us like this process ends, but not to the people who live on the hyperbolic plane, because decreasing y0 actually makes this length arbitrarily long. So postulate number 2 holds on the hyperbolic plane for these geodesics, okay, for the vertical ones. So what happens if now I take a geodesic that is not a vertical line? So let's take A and B, not vertically aligned. So how do I produce the geodesic? As always, connect these two, take a perpendicular bisector, and this will give me a center of a circle. So so this is the geodesic, right? Joining A and B. So what can I do with this geodesic? Can I extend it indefinitely in both directions? Again, it looks like I can only do it in a finite way, because this semicircle is of course a finite creature, but it's only finite to us who have this skewed map of the hyperbolic plane. Again, these parts of the circle, as I keep extending them down here, from the point of view of the inhabitants of the hyperbolic plane, it looks like this process just never ends. And in fact, let's again do a similar calculation here. So what happens now? How do I measure the distance between these points A and B? So I draw these rays. So let's say this angle will be beta. and then there's another ray here that goes to A. And this angle here is alpha. And now the distance between these two is the natural log of the cosecant of alpha minus cotangent alpha divided by cosecant of beta minus cotangent beta.